converted our hypersonic test facility in Plumbrook Station in Sandusky to NASA Electrified Aircraft Testbed, NEAT. Currently, this state-of-the-art facility is being used to test full-scale megawatt powertrains with an eye towards incorporating component technologies into an overall system. The facility can support single-aisle aircraft geometries with proper cable lengths and electromagnetic interference mitigation. It can supply power for up to 24 megawatts, thermal management system for up to 2 megawatts, and it even contains an altitude chamber that can simulate up to 120,000 feet. All electric aircraft concepts that we've seen so far rely heavily on advancements of components such as advanced motors, power converters, and material science, to name a few. X-57 work is an example of much larger research portfolio within the field of power systems led by NASA Glenn. Over the past 20 years, Glenn has pioneered designs of various high power, density, and high efficient motors for space, aeronautics, medical, and terrestrial applications. All our work has always pushed the boundaries of what's possible, and our newest motor work is no different. NASA Glenn has a small in-house team that is developing a 1.4 megawatt motor with a performance goal of 16 kilowatts per kilogram and efficiency greater than 98%. The motor contains a self-cooled superconducting rotor, which has never been done before, allowing the motor to achieve exceptional specific power and efficiencies without inheriting external cooling weight penalty commonly attributed to superconducting machines. Integrated rotor superconductor, spinning at 6,800 RPM, 4 times higher than the state-of-the-art, and weighing only 80 kilograms. This motor revolutionizes the field of advanced motors and greatly increased number of aircraft concepts that can utilize hybrid architectures. All our electric motor work is all diverse in size, applications, and power levels. And it's beyond the world of aeronautics. Just 5 years ago, my team designed, built, and delivered a biconical motor to University of Indiana School of Medicine. This motor was designed to help catalyze advancements in the field of cardiovascular assist devices, such as pacemakers for kids who are born with a single heart ventricle. This motor is tiny in comparison to the ones on aircraft, just 2 inches tall, and is powered by a total of 5 watts, same power as USB ports on your computers. Currently, our design is being used to develop a clinical trial version, and hopefully a viable device will enter a market within a decade, saving an estimated 1,500 children per year. All great progress is accompanied with great difficulty and must be enterprised and overcome with answerable courage. In our efforts, we don't underestimate the power of vision and direction. These are irresistible forces able to transform what might appear to be unconquerable obstacles into traversable pathways and expanding opportunities. I am deeply humbled to have an opportunity to be part of this amazing journey, a journey that will surely.
Imagine if you were an alien who, was visiting the Earth for the first time from some other galaxy. Imagine only visiting the United States and never visiting any other part of the Earth's surface. That's essentially what we've done with the Apollo missions. Really been able to do wonderful and groundbreaking science with the samples, collected during the Apollo missions. But again, we visited only a very small part of the lunar surface.
The way that I think about it is it's the equivalent of landing on Earth and getting rocks from Kansas. It would give us insight into one particular location on the Earth, but not at all the diversity of what we see on the Earth, what we know is present on the Earth. So the ability to go to a different site, a different location, get different samples will just enrich what we've already learned from our Apollo samples.
There's a lot left to be learned about the moon, and it starts with the South Pole.
Artemis astronauts will fulfill a different mission in a unique environment. While the Apollo astronauts who visited the moon's surface between 1969 and 1972 landed near the equator, Artemis astronauts will venture to the moon's South Pole region. Frigid, rugged, and with unique light and darkness conditions that make it an ideal location for exploration. The South Pole region is also home to the rim of the moon's largest, oldest, and deepest crater, called South Pole Aitken. It takes up almost a quarter of the moon, and is so deep it exposes portions of the moon's interior.
Yeah, the South Pole it's fascinating. There are some very unique types of rocks that are at the South Pole that will allow us to understand the entire history, not just of the moon, but potentially of the solar system.
Very early on in lunar history, we think that there was this increased period or very intense period of huge material hitting the surface of the moon, creating these really large craters or like giant holes, which we actually call basins. So getting a sample of impact melt from this basin would kind of help us bracket that early period of time.
The moon's South Pole region has resources that are vital for long-term exploration. Because the moon is barely tilted relative to the sun hovers over the horizon at the South Pole. Imagine a flashlight turned on, laying on a table. That's how the sun illuminates the South Pole. Light at the South Pole strikes at such a low angle, it brushes only areas of higher elevation, such as crater rims. These locations have sunlight for extended periods of time to harness for power. At the same time, the bottoms of some deep craters are shrouded in constant darkness. Scientists have measured the coldest temperatures in the solar system inside these craters, which have become known as perfect environments for preserving water for eons.
Over time, there's individual molecules of water and carbon dioxide and other gases that actually bounce around the surface of the moon. And when they get to one of these cold spots, they actually get stuck. So we call those places cold traps. And if you do that for millions and even billions of years, you can actually build up a pretty significant deposit of water and other ices.
From an exploration perspective, if we can understand just how much water there is and where it is and how to get it out of the regolith of the moon, we can turn it into really important things like drinking water for astronauts and even rocket fuel to take them back home. So really understanding these resources and how to use them is one of the objectives of the Artemis program, and it's what makes the South Pole of the moon so exciting.
We know the moon in incredible detail, thanks in large part to NASA's Lunar Reconnaissance Orbiter, or LRO. LRO has been circling the moon since 2009. It's the longest-lived spacecraft there. Through tens of thousands of orbits and data from 7 instruments, LRO has mapped the moon's temperature, geology, radiation environment, and is providing insight on how the moon is changing over time. LRO is led by Dr. Noah Petro, a planetary geologist at NASA's Goddard Space Flight Center.
LRO is this incredible mission. It was launched in 2009 as the opportunity to go back to the moon, to create this three-dimensional, high-resolution, high-definition atlas of the moon. Where are there safe landing sites for human and robotic explorers? So what LRO is doing is really giving us the tools, the material, the data we need to make those missions successful.
For many years, LRO's elliptical orbit was closest to the moon during the spacecraft's pass over the South Pole. So scientists have more information about the South Pole region than any other region of the moon.
We know that we can do more and build upon the legacy of Apollo. But to do that, we needed a higher resolution data set. We wanted to know where the hazards were. We wanted to know where the geologic features were that we want to go explore. And so LRO has created that database. Incidentally, the LRO data volume is now over 1.3 petabytes. It's the largest volume of data that NASA has ever collected from any planetary body. It's remarkable. And what we've done now in support of Artemis, in support of other NASA missions to the moon, is we've created special maps. We share them with the public and we share them with the various engineers and scientists who are going to help enact and make Artemis a reality.
You know, this is basically a Google Maps of the moon, taken from pictures from the Lunar Reconnaissance Orbiter camera, and you can just zoom in and see a 5-meter boulder on the surface of the moon. That's just crazy. I could spend all day, and I have spent all day, sometimes just browsing around different parts of the moon, just looking at air rocks.
This wealth of information will make it easier to find ideal locations for a NASA base camp, and to quickly identify scientifically interesting areas to visit nearby.
So it's my real belief that we have an opportunity with Artemis to do something different than Apollo. We build on Apollo, we learn from Apollo, but we want to expand what Apollo was able to do and build this presence on the moon that is more than just 3 days, more than just 6 individual missions, but a much larger program that eventually will result in the ability to go onto Mars.
Mars is quite a bit longer away from our own planet than, of course, the moon is. It takes several months in some cases to get to Mars, and it's therefore going to be really critical when we have astronauts walking around on the surface of Mars to be able to stay there for longer periods of time. You've just spent 6 or so months to get there. You want to really be able to explore the surface around you, and having the ability to live off the land and know how to conduct exploration for longer periods of time is going to be critical for Martian exploration, and lessons learned for that sustainable type of exploration start right here at the moon.
So there's still so much for us to learn from going back to the moon from a scientific perspective. It's a no-brainer in my head. So with Mars in the horizon as our kind of end goal, this is an important step for us to take. And then also just kind of from a human aspect, we all have this kind of intrinsic desire to explore. I think it's in all of us and certainly in us as a society. And so I think setting our sights on something and accomplishing this goal together is really important just for international relations, for, just coming together as a humankind, the human spirit. I think that's a piece of what we're doing that we can't ignore as well.
I have 3 kids, aged 10, 6, and 2. I talk about space often with them. The great thing that my parents did for me was let me find my path. I also look at my daughter, and I think, okay, Amelia, she keeps saying she wants to be a firefighter, a construction worker, and an astronaut. And I said, well, Amelia, you can do all 3 and be an astronaut. Well, when you're an astronaut, you gotta learn how to fight a fire in space, you gotta learn how to build stuff, so you gotta do all those things. What they'll become, I'm so excited to find out, but I have no idea what they're gonna end up gravitating towards.
So why is the moon my favorite body to study? I think growing up, you could always see it in the sky. You could see some beautiful stars and maybe Mars or Jupiter as like small little dots, but the moon is just there in all its glory. It's like our nearest and dearest neighbor, and you can even with the naked eye, you could start picking out features on the moon. I think that was really cool. This is thousands of miles away, and you can still kind of be a geologist from the ground if you want to, and I think that's really cool, and that's why I always wanted to study the moon. Just seeing people walk on the moon, on this foreign planetary body, looking at images like the one behind me here, I think that always blows my mind.
I will say with my 2-year-old, what I have noticed recently, and this is wonderful, is that when he sees the moon, we're out for a walk, we're driving around, or outside a window, we go, moon, moon. And just the fact that he can look up and see, go, oh, moon, moon, that makes me so happy.
Greenland. A massive ice-covered island in the northern Arctic, a land of pristine waters, enormous glaciers, and ancient geology, and for some, the site of a hotly contested claim of the oldest signs of microbial life on Earth. Meet Dr. Abigail Allwood, astrobiologist at the NASA Jet Propulsion Laboratory. Dr. Allwood is here in Greenland to investigate recently published findings of possible stromatolites, or microbial fossils, dating back to 3.7 billion years ago.
It's always when I go and see some rocks and outcrops in the flesh, it's so much more eye-opening and informative than it is to read about them in papers. And absolutely the case with this one. When I came to see them after that paper was published, I very much doubted that interpretation, and I thought, well, we need to do two things. One, we need to put a paper out, and secondly, we need to do a workshop and bring a lot of people out here to also see what their opinion is, reach some sort of a consensus on what the right interpretation was.
Extraordinary claims require extraordinary evidence, and a finding like this requires further investigation. Dr. Allwood has gathered a team of astrobiologists and will now travel by helicopter into the wilderness of the Ishua Greenstone Belt.
So we're out here to study an outcrop that there is some controversy over. There's a group of authors that has made a claim that there are biosignatures in the form of stromatolites in these rocks. And there's another group of authors, I happen to be one of that other group of authors, that has refuted that claim. So we're out here in Greenland to study those outcrops in more detail and to try to get a sense of the geology that surrounds those potentially stromatolite-bearing outcrops and try to get a sense for what the ancient environment looked like at the time that those rocks were forming. The claim was such a big deal because if it proves to be true, then this pushes back the earliest signs of life in Earth's geological record by a couple of 100 million years.
It means that the window of opportunity for life to emerge doesn't have to be very big. Literally, as the last bombardment is occurring, that you can say that life can take hold. At least our one example that we have that life took hold. Go to Mars. It means that it only also had to maintain its conditions, its sort of cradle of life, its opportunity for life to emerge for that short period of time. It didn't have to sort of maintain it for a couple of 100 million years longer.
And when you go back to those very old rocks, they're usually altered and deformed, and it's very difficult to find those signs of life. But those are also the most interesting rocks to look at because we don't know when life originated on Earth, and we don't know what that earliest life was like. So the record that we have from geology is in these rocks that are very difficult to interpret.
Wonder which way I'm going to put it. Okay.
Sampling here in Greenland is, it's not all that different from sampling anywhere else. A geologist's tools are kind of the same no matter where you go. You need a hammer, a chisel, a little, hand lens to look at the rocks up close, field notebook, camera, and you record your observations, and when you think you've zeroed in on a piece of rock that might be worth taking back to the lab, you get your trusty rock hammer out and just start banging away until the sample comes out.
When we're looking at rocks, trying to understand if they preserve evidence of life, we look for things in the rock that cannot form without the influence of life. They can change the chemistry, and they can actually change the shape of the ground. And they can make things like peaks and domes that are sometimes unique to the biology.
again, I think here what you need to do is look at the context of the rocks around those stromatolites and try to get a sense for what that geology is telling you.
This is our sample here. Came from the outcrop. We've got that new sort of cut and polished base there. And if it was really a cone-shaped structure, then you shouldn't see it on the back of the sample. You shouldn't see it in the back of the hole there. That's about 14 centimetres depth hole, and you're still seeing the structure there. So it's not a cone, it's a ridge. If you can sort of reconstruct that in your mind. Got to prove the three-dimensional morphology. Absolutely have to prove. It's the same story. You can see the structure at the back of the hole there. It's maybe 15 centimetres or so. It was present at the front and it's present at the back, so it's at least that distance in length. It's not a cone shape at all.
A lot of times when you're looking for something that's related to Earth history, I think of it as being like I'm a detective and I'm looking for clues. But the thing is that the rocks are not very good at preserving clues. And my job as a geologist is to take those little bits of information and see if I can make a story about what happened in the rocks. Part of making that story, though, is understanding the uncertainty. The story is never complete because you're always missing a lot of the clues because the clues have just been lost through time.
After investigating the site thoroughly, the team concludes that there is insufficient evidence of life in these structures. However, there is still much to learn from the geology in this environment.